its RMS value on the box. If you display a histogram of the data that's coming out, it's not going to look bell-shaped like this. In fact, it's going to, there's not much useful information, okay? So I'd like to talk a little bit about that. So there is a famous formula, and this is, if you take an analog to digital converter, and this has nothing to do with whether it's delta sigma or a flash A to D or any of those types, if you put in a full-scale signal, and I'm just going to pick an arbitrary value, a sinusoid of full-scale value, and let's say that that happens to be between plus 1 volt and minus 1 volt. So this thing has a 2-volt input dynamic range. I just picked that out of the air. And you digitize it, obviously, with a number of bits n. Okay, 8-bit converter, 12, 14, or even the 24-bit that we're talking about. There is a formula that's, if you look at the output of this signal, you notice that if you just imagine for a minute that you take the digital output and then route it back into a digital to analog converter. So if you run into a digital to analog converter, your signal would appear like that. Because it's been quantized by the A to D converter. Does that make sense? So if you had, on an 8-bit A to D converter, you're only talking about 256 individual levels. So if you've got 2 volts here, between plus 1 volt and minus 1 volt, if you run that into an 8-bit converter, you've got only 256 numbers that can represent that. So each one of those is going to be quantized. These steps are going to be 8 millivolts apart, roughly. Okay, 2 volts divided by 256. So about 8 millivolts apart. So, that's actually getting to where it's observable pretty easily. Of course, we're not getting into anything about how fast this converts or anything like that. So just assume that everything works perfectly. Well, this signal has obviously got some errors in it, and it turns out that there's a famous formula that the signal to noise ratio of the resulting signal is equal to 6.02 n, where n is the number of bits of the converter, plus 1.76 dB. So even if the converter works perfectly, no noise, everything about it is perfect, that's what you'll see in the best of circumstances. So, this is, I'm showing you now something that is very definitely not a sigma delta converter. This is an old converter of the flash type here, and so you can see that the analog input is fed in to a whole stack of comparators here, and your reference voltage is then just divided down by a bunch of resistors. And so if you need to implement, for instance, an 8-bit, this is called a flash A to D converter. If you need to implement a flash A to D converter, 8 bits, you need 256 very well matched resistors in order to divide that voltage up. And then basically, whatever your voltage is, you get a thermometer code out. The analog input is, zoom out for this. The analog input's higher than this one, higher than this one, higher than this one, higher than this one, da, 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 and then it's not. So you get a thermometer code here, then you put it into a decoder, and that decodes your work. These are old-fashioned, they've been around forever. They're incredibly fast, right? Hence flash. So this is a flash A to D, and that formula right there of the signal to noise ratio of the output signal due to this induced quantization noise is valid for that one. As well as a sigma delta A to D converter. So they're all equally noisy in that respect. Quantization is just a fact of life. If you're interested in how to take the mystery out of how this formula is derived, I posted this from Analog, taking the mystery out of the infamous formula SNR equals. So this talks about it, and by the way, the seminal paper that was written in this area was written in 1948. So they were pretty forward thinking then. I believe it was Bell Labs, and clearly not thinking about 24-bit sigma delta A to D converters at that time. There, this derives it, and it basically shows what I'm showing there. If you have, say, not a sine wave, but just an increasing signal, it gets quantized in steps like that. And the difference between those two, the error of the signal there is this little sawtooth wave. So if you put a ramp into an A to D converter, the error between the output value and the input value is a sawtooth wave like that. And so it's actually a coherent signal in that case, but if you interpret it as noise, the ratio of the signal power, the sinusoid power, to the noise power, the sawtoothy part in there, is this, right? And so, obviously, the bigger N is, the bigger your signal to noise ratio is, because these quantizations get more and more accurate, right? And so with the 24-bit A to D, with the 24-bit A to D, I mean, 6 times 24, that's an enormous signal to noise ratio. Right? This is dB, right? So that's huge. So the problem is A to Ds have other sources of noise besides just the quantization noise, including comparator. If you look in this type of system, this is all predicated on the fact that each one of these little amplifiers, the input offset voltage is the same. There's all kinds of nonlinearities in there, and typically what you actually get at the output is a combination of noise and distortion. So it's pretty common that what we measure is the signal at the output, and then we say N equals the signal to noise ratio minus 1.76 all over 6.02. And in a perfect world, N is the number of bits in the converter. But if your signal to noise ratio is not as good as the perfect one, then you get a lower number N. So for instance, if you have a 24-bit A to D, but your signal to noise ratio comes out, I can't do the math in my head, but if it comes out that N is only 20, that means your effective number of bits is only 20, not 24. So this is the thing you can measure, SNR. Adding to so N here is actually the effective number of bits, effective number of bits. And you'll also see this formula written a little bit differently because it's very hard to separate noise mechanisms from nonlinearities. You'll also see this as, not SNR, but you'll see this written as synad minus, and synad means signal to noise plus distortion, which is what you really end up measuring. So your signal to noise plus your distortion minus 1.76 in your signal to noise ratio in dB minus 1.76 divided by 6.2 is your effective number of bits. And again, you don't really need to know the ins and outs of this theory. All you need to know is that these very accurate oversampling converters like sigma delta ADs rarely achieve their full 24 bits of signal to noise ratio. In fact, even a lot of 12 bits only resolve about 10 and a half. So that's what that means. Now notice that this signal, this is predicated on the fact that what we put in here for a signal was full scale. In other words, +1 was the maximum input that the A to D could take, and -1 volts was the minimum. So that's a full scale. If your signal size goes down, what do you suppose happens to your signal to noise ratio? That's almost a tautology, right? If your signal to noise ratio is measured and then your signal gets smaller, what happens to your signal to noise ratio? It goes down, right? So we have to have a standard to measure the signal to noise ratio at, and the standard is we usually use a sine wave well within the frequency of operation that we expect this thing to work at full scale. It only makes sense to compare apples to apples, so we measure a full scale sine wave. For the kinds of things that you would apply what we're building in this lecture, in this course, that really doesn't apply because we have a problem here. What happens for a DC signal? For a DC signal, your amplitude goes down to 0, and so your signal to noise ratio goes to 0, which means you have no effective bit. So it's not the right formula for measuring DC quantities. So that's where the other part of your design. So this business about a histogram. And one of the videos from TI, I gave you the timestamp to go to. It shows you this being done exactly. But let me give you a little bit of an example of this. Suppose we had, let's keep it simple, and we had an 8-bit ADC. And let's, again, assume that its input range was from +1 to -1. But DC. Let's now ground the input. So we can have the output here can display anything from this number here can represent anything from -1 to +1 volts. And so if we're going to pick an 8-bit here, that would be 1, 2, 3, 4, 5, 6, 7, 8. The smallest number this can represent represents -1, and 1, 2, 3, 4, 5, 6, 7, 8 represents the +1 volts. So if we ground the input, where do we expect it to be? Right in the middle, right? So if we started collecting data points at our sampling rate, if everything was working perfectly, we would get just a whole bunch of bins here at whatever, 0, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, right in the middle. Well, unfortunately, the ADCs are noisy. So the proper way to measure the signal to noise ratio of the ADC itself to a DC input, where this formula is no good because the signal is the signal noise ratio is 0. So in this case, what we look at is, well, this thing, we're now talking about the ADC generating its own noise. So occasionally that's going to count 1 here, and so you simply add up the bins, and if it behaves like most noise processes, you end up with kind of a Gaussian distribution. Now again, in this example of an 8-bit ADC with a 2-volt input range, these bins represent 8 millivolts apart, and the noise is going to be less than 1 millivolt probably. So you won't actually see it happen. But you will in a 24, for sure. So if you display this, so this is literally the integers, the base 2 numbers that represent everything here. You should get a nice bell curve. And in a 24-bit A to D, you'll get a nice bell curve centered around 0 because we grounded our input. If you put a sinusoid in here, then you get a messy, right? They're all over the place. So that's no good. So this only works for this grounded input. If you look at the standard deviation of this in terms of least significant bits, how many LSBs is the standard deviation of this? Then n, the number of bits in your converter, minus log base 2 of the standard deviation will give you the effective number of bits. And again, this is all in the TI video. So that's what for Gaussian type noise, that's what we want to measure. So if this ADC is designed to measure quasi-DC signals or low frequency signals, then its noise is best measured in this way. Now, instead of connecting this to ground, we're going to connect it to our device under test, which is some noisy op amp or something. The noisy op amp, also grounded. We're picking something like the 741 where you have a heck of a lot of noise coming out of it. And so you're in fact also going to get a bell-shaped curve, just your counting of occurrences. It'll be much bigger and much wider. Obviously not from -1 to 1, but much wider. Okay, so you simply have to look at this, assume that it's more or less Gaussian, figure out its standard deviation, and then you can figure out the effective number of bits, which will be n, the actual number of bits, 24 in your case, minus the base 2 logarithm of standard deviation. So this is the appropriate way to do it for DC. So the nice lady from Texas Instruments in the video will explain this using all kinds of engineering jargon, but that's basically what she's saying. Any questions? So this week, finish up with your preliminary proposed disposal. Your preliminary disposal